Hello everyone, these are the notes for topic 1.4, composition of mixtures. In this set of notes we will be looking at how pure substances contain molecules or formula units of a single type, but mixtures contain molecules or formula units of two or more types. Of two or more, I think that's supposed to be an or, whose relative proportions can vary. Okay, so we're looking at mixtures here. Elemental analysis can be used to determine the relative numbers of atoms in a substance and determine its purity. So we're going to focus on those two in these sets of notes. So let's get to it. When two or more pure substances, which are elements or compounds, are combined, they form a mixture. You mix milk and cereal, it is a mixture, though technically those two are also mixtures as well. Okay, in mixtures, the composition can vary. Like you do your bowl of cereal, and all the milk's at the bottom, and all the food's on top. And then you got dry bits that are hanging around at the tippy top, and you're trying to get them wet and squishy. There's the insight into my breakfast life, guys. The mixture can be analyzed in order to determine the mass composition of each substance in that mixture. You can use stoichiometry, mole ratios, to convert the masses of the products from the analysis to determine the amounts of reactants that were given in the original mixture. Okay, and so we have a little mole map here to help us with that. The mass percentage of a substance in the mixture can be calculated using this formula. Notice that it is very similar to the percent composition for compounds, but this is like percent composition of stuff in a mixture. Okay. Elemental analysis is used to determine the composition of a mixture. This can be qualitative, which allows you to identify the elements present, or quantitative, identify the amounts of each present. Elemental analysis is part of an analytical chemistry, okay, analyzing the composition or chemical makeup of stuff. There are various types. The CHNX, which is carbon, hydrogen, nitrogen, and other compounds, is used primarily by organic chemists to identify the mass fractions of carbon, hydrogen, nitrogen, and other atoms such as halogens or sulfur. One form of this is called combustion analysis. All of the carbon in a sample is converted into carbon dioxide, and all of the hydrogen is converted into water. Nitrogen is converted into nitrogen monoxide or nitrogen dioxide, and sulfur, as an example, is converted into sulfur dioxide. And so then they look at how much of each one is produced, and that allows them to determine how much was originally present in the sample, because it's in a closed container, so nothing else is in there except oxygen. And then they light it on fire in a closed, controlled system, so you don't lose any of your carbon, hydrogen, nitrogen, or other elements in the compound, and you don't accidentally add contaminants either. Then we have spectroscopy, and there's a few different ones. We have optical, so lights pass through a substance, and we'll get to that when we look at Beer-Lambert law in 3.13. We have mass spectroscopy, which we looked at that in 1.2. And then we have photoelectron spectroscopy, which we are going to look at that a little later in this unit. Okay, we looked at that last year as well. So now we're going to move on to some I-dos using this concept of percent composition of mixtures. So aluminum metal reacts with the air and forms a thin, corrosion-resistant coating of aluminum oxide, according to the following unbalanced equation. So hopefully remember to balance our reactions. A sample of a mixture of aluminum and aluminum oxide weighing 120.91 grams was analyzed and found to contain 20.32 grams of aluminum. We have a series of steps that we're going to take. These are organized in the order that you should do them. Okay, so our first one is to balance the equation. So I'm going to rewrite the equation. Aluminum, so Al2O3. I'm not writing the state symbols because they're not important right now. I just need to balance the equation. When we start doing gas laws and things, it's going to be important in equilibrium to note what the state of matter is, but we'll get there when we cross that bridge. So reminding you of how you should take inventory. So I have 1 and 2, and you might do this a little different, and that's fine. This is how I'm doing it, and I'm just going over a method. Okay, so 1 goes into 2 times, so I'm going to write that 2 there, and that now matches. 2 does not go into 3 evenly, and oxygen is in just one spot on both sides, so I'm going to use least common multiple. Out of these 2, least common multiple is 6, so I'm going to make both of these 6. So 3 times 2 is 6, and then over here 2 times 3 is 6, but that also changed aluminum to 4. So I need to go over here and fix this and change it to match, and now I need 4 here, and that is now 4. Okay, so that is now balanced, and so I have my balanced equation. Okay, so now we're going to look at B. What mass of oxygen was in the sample? So I know that my combined mass of aluminum and aluminum oxide had a mass of 120.91 grams. Okay, so the total mass of everything was 120.91 grams. And I know that the aluminum component of that was 120.32 grams. So I know what the total mass is and what the mass of just aluminum is. So I can subtract the 2 and find out the total mass of just oxygen. And so that is 0.59 grams of oxygen, and that's O2. So now it wants to know what mass of aluminum oxide was in the mixture. Well, I know how to relate oxygen and aluminum oxide to each other because I have this reaction and I have oxygen, I know for sure. This aluminum mass that's here is going to be both the aluminum from just the aluminum solid and aluminum from the aluminum oxide, so it is not pure. But I can use my known mass of oxygen to convert it to aluminum oxide and know how much of the aluminum oxide I have. So, starting there, I'm going to take my grams of oxygen, and I'm going to first have to convert it to moles of oxygen. Sorry. And then I know on the bottom I can put grams of oxygen and that this is the molar mass. So 1 mole of oxygen has a molar mass of 32.00 grams of O2. That's 2 times 16 because I have 2 oxygen atoms in the oxygen molecule. Now I want to get rid of the moles of O2 because I don't need it. What I really want to know is stuff about aluminum oxide because that's what the question asked me about. Well, I'm going to look at the mole ratio between the two. And when I see a mole ratio, I know I need to look at the balanced chemical reaction to get my numbers. So I pull the 2 for aluminum oxide and the 3 for oxygen. So I know my mole ratio between the two. And so from there, I can take my moles of aluminum oxide and change it into grams of aluminum oxide. And I can't do that super easy, so I need to go and determine the molar mass of that. So that would be 2 aluminum plus 3 oxygen. And you guys can do that yourself, but I can't remember what the molar mass of aluminum is, but we're going to wing it. I do know that the molar mass is 101.96. I'm saying I did not write it down because Miss Burt was super smart. So 2 aluminum plus 3 oxygen is equal to 2 times 26.97-ish, I think. And then, or 93, looks like it might be 93. Nope, 96. Plus 3 times 16. I'm pretty sure that those are the numbers, but I want you guys to go back and do the calculations. And then that should give you 101.96 grams per mole of aluminum oxide. Okay, so you want to check that molar mass before you finish, but there it is. And then that is the mass of 1 mole. So then when we run the math, we multiply by the top, divide by the bottom, cancel units out. And you should end up with 1.3 grams, and we know it's 2 sig figs because our starting quantity is 2 sig figs of aluminum oxide. Okay, now from there we can determine D, which says what is the mass percent of aluminum oxide in the aluminum and aluminum oxide mixture. So we're going to start with D. Okay. We know that the mass of aluminum oxide, what it's asking us about, is 1.3 grams. And that the mass of the total sample was 120.91 grams. And since we're looking at a percent, we're going to multiply this by 100. And so you should get that the percentage is 1.1% aluminum oxide. And remember, even though it's really thin percent composition, it's supposed to be a very thin layer over aluminum metal, right? So it should be a thin layer that just protects the rest of it. Okay, now looking at the we do. Oops, too far. The main component of eggshells is the compound calcium carbonate. If you react eggshells with acetic acid from vinegar, so you're doing vinegar and eggshells, the following reaction takes place. If we have 4.421 grams of carbon dioxide produced from 10.57 grams of eggshells, what percentage of the mass of eggshells is calcium carbonate? Okay, so you are given carbon dioxide, grams of carbon dioxide, and you are given the total mass of eggshells. Okay, so you want to know the percentage mass of calcium carbonate, right, in the eggshells. So we are going to, as a hint, you're going to start here with your known value of a specific part, right, because it's in here. And since there's a coefficient, you can assume that the reaction is balanced. So we have a specific part, and we can change that into the mass of calcium carbonate, and then determine the percent composition. So what I want you to do first is to figure out from the 4.421 grams of carbon dioxide, how much or what mass of calcium carbonate did it come from? So what is the mass of calcium carbonate in the eggshells? Go ahead and pause the video, please, and work on this first step. Okay, So doing the first conversion, you should get going from grams to moles of CO2 to moles of calcium carbonate to then grams of calcium carbonate using molar masses. You should get 10.05 grams of calcium carbonate. Remember to drag units diagonal so that they cancel. Okay, and you go step by step using the mole map that we learned in your first year chemistry class. So now we know how much calcium carbonate we have in our eggshells. Now we can use that and the total mass of eggshells here to determine the percent composition. I want you to pause the video and practice that now. Okay, so you should get that the smaller number, the calcium carbonates on top, and this should be 10.57, grams of the eggshell on the bottom. And when you divide those, you should get 95.12% calcium carbonate. Okay, using these, you're going to complete the you-dos, and remember that the answer keys will be available for you in class to check your work. Thank you, everyone.